Welcome back. In this clip, we'll talk about the secondary particle trails. So for that, we need to select the n particle 1 and we can go inside the n particle menus, go for the emit from the object command, and we have the emitter type set to the omni. Let's reduce the particle count to, let's say, 100 and hit the option create. But very important thing, before we go for the creation, let's do one thing. Let's change the solver from the nucleus 1 to a new nucleus, because I have experienced, if we create this similar particle object which is emitting from the first particle having the same nucleus, it can create some issues. So it's better to be on the safer side and we use a different solver. Alright, now hit the option create. Now once we create this, let's roll the timeline back and let's play this. So we can simply see the particle trails, but you can see some different kind of behavior. This is just because of the gravity. So simply select the n particle 2 and go to the dynamic properties where we have ignore solver gravity, not a problem. And let's also increase the the lifespan of the particles. Let's say we'll go for the constant and use lifespan as a 3.5 to maybe, let's say, 4. Alright, now let's simply play the timeline, and here we have some nice trails. And let's do one thing. Let's also change the particle render type from points to the sphere so that we can have some some more meaningful forms of the droplets. So let's go inside the particle render type and change it to the, either you can work with the sphere as well as the blobby. Alright, not a problem. So I prefer to go with the blobby surface. This is a new type of the particle render type, and we'll make this utilized while converting these particles to the polygons. So we'll do that a little later. Alright, now let's concentrate upon the overall shape, the natural properties of the droplet. So right now it's simply giving me a sense of some straight lines getting created and simply just making no sense. So let's do one thing. Let's first of all select the n particle 1 and change the particle render type to the point, so that we can able to differentiate between the n particle 2 and n particle 1. So the trailing particle here is the n particle 2. So let's do one thing. Let's add a per particle attribute, that is the radius pp, and let's control the overall radius of the n particle 2. Let's move inside the per particle attribute and select the n particle 2. Over here we have, go to the general and now select the radius per particles. You can go inside the particle tab and click the radius pp, hit the option. Okay, now just simply right click and go for a ramp and go for the edit ramp. Now you see we have some 3 color entry lists. Get rid of the mid one and change the interpolation type to the exponential down, and drag a color generally of a gray and just slightly increase the value. Pick a mid color and add it over here. So now if you play, you'll notice you can now have some better form of the drops. But yeah, I definitely agree that the droplet size is way too much high. So instead of controlling the droplet size from this color entry list while working upon the color values, which is over here, I prefer you can go inside this input output connections and use the min and the max value. The min and the max value basically controls the values of the ramp which we are using for the radius pp. Now let's say if we have the maximum value which can touch to maximum 0.4 and a minimum value instead of 0, let's say 0.125. So now if we play the timeline, you can see we can have some more sensible forms of a droplet, and this is something which is very nice. But we have a lot to cover, because I totally acknowledge that in this case we don't have some interesting fickle inside the drop, because first of all, right now all these droplets are sliding from this glass with this constant speed and all, and there is absolutely no interest we can have inside the motion of this droplet. So let's do one thing. Let's also reduce the max value to maybe 0.35, maybe 0.3, and that we can take care of this thing a little later. And I think so this is looking much better. Yeah, that definitely. So now the most important thing is that how can we control the fickle of the particles, because these are first of all just getting dropped. It's not showing any realistic behavior. So the main thing is that it's the n particle 1 which is, driving the n particles too. So if we want to give some nice and interesting changes, then obviously we need to refer to the n particle one. All right. Now let's do one thing. Let's work upon the n particle shape one dot goal u. All right. Let's work upon the goal u attribute of the n particle one. So we can go inside the expression editors and pick this n particle shape one. So let's say we have n particle shape one dot goal u plus equals to, let's say we have, point 0.01. All right. And now if I play the timer, you can see that, this is happening. So this is obviously, I'm not, looking for this kind of an effect. So now let's pay attention, guys. Now we can fix this if we use an expression that is the noise. So noise is a function that returns the value, a random value that ranges from 1 to the -1. All right. So let's have a noise. All right, and we'll put inside a value that is the random value. So we can also use a spherical rand. So I'll tell you what exactly is this. So first we write it is spherical random. So this creates a 3D sphere, and whatsoever value you enter inside this will be the radius of the, a 3D sphere, and the maximum value of the range is the radius and the minimum value is the 0. So values will be randomly distributed from 0 to whatsoever value you enter. Let's say if I enter the value, let's say time plus the ID of the particle. All right, pretty straightforward. Now let's close the bracket, hit the option, semicolon, to terminate this. And this is the function noise which we have, and inside this we have a sphere rand time plus ID. Hit the option edit, not a problem. Now if I play the timeline, you can see, yeah, something is happening, but this is also kind of a, very bad kind of thing is happening, and something which is totally out of control. So let's do one thing. Let's control this. So now let's go for the noise expressions over here, and let's say we multiply the entire thing, with the help of some smaller values, which will be the amplitude of this, whole expression, or you can say the function noise. So let's say we multiply this with the help of 0.00, let's say 15. All right, and hit the option edit. Now only from these small changes over here and over here, what I have now, if I play the timeline, you'll notice something nice will get started, and this is really very nice, I should say. Now we are actually getting the realistic behavior of the drops that happen. It's simply a very simple logic. We have kept the value of goal u plus, which is equals to the noise, and this is actually a formula that I'm utilizing. So let's say, this particular value is very important, and this is the amplitude. So what if I just increase the value to maybe 0.0025? And one more thing, guys, this is really very sensitive thing. All right, now hit the edit and just play the timeline, and now you'll see we have some more, interesting, but the particles are showing some more fickle. The distance is actually a little bit more high. So what if I just, increase the value to maybe, let's say 0.0055, and now notice the change. Now in this case, you'll see the particle will take some more bigger turns. So now it's totally up to you guys. I would like to leave this thing up to your artistic decisions. All right, now let's do one more thing. Instead of having bigger values of, let's say we have 0.0025, and let's multiply with the frequency multiplier. We can also introduce another value inside this, inside the formula of the noise, to increase the frequency, so that we can have some more repetitive pattern of this fickle, a horizontal fickle. So let's say I multiply this thing with 0.25, maybe, hit the edit. Now if I play the timeline, you should see, well, actually the particles have become more slow. This is not the way we want. We just want some higher frequencies. So instead of multiplying with such a low value, let's multiply with the 2. All right, and now if you play the timeline, you should notice we have some more nice and interesting shapes. But I agree that this is a quite exaggerated, so maybe I don't want that kind of a big change. So let's do one thing. Let's go inside this, and let's just reduce this value to maybe 1, or maybe let's say 0, and hit the edit. So with this, the overall amplitude will be reduced, and I think so this is looking really very nice. So we can change the value till the moment these particles won't have a kind of a spacing inside them, or I mean, aesthetically they should look good, and technically they shouldn't be having some, spaces or gap. That is something which is very, very important. Let's do one thing. Let me show you some errors. What if we have such a high value? Now notice one thing. If you go for a very high value, then we have something like this. So this is, just a kind of a crazy workflow. But I just want to show you that, guys, how much control you can get inside your particle. So this is something really very nice and, really really very amazing. So that's the power of the expressions. If you add to your simulations, you can take the things absolutely to the next level. However, we don't want to have an effect like this. So let's do one thing. Let's decrease this to a value of 0.0010, and let's say the frequency is to be 2.5. Not a problem. Hit the edit and I'll play the timeline. And here we have, and I think so this is one of the most beautiful things, I should say, in terms of the droplet. All right, now we have covered the horizontal fickle inside the particles, but there is another one important thing, and that is the vertical fickle. So let's do one thing. Let's take a pause over here, and I'll continue the same subject in the next clip.